Welcome to another unit of the ISM course in Statistics 2. This time with a unit on set theory. So basically we need the results we get in this part of the course to better understand how different types of probabilities, or more or less if two events happen at the same time or one after another, how they result in different other probabilities. And for this, well, we start with simple assumptions. Relatively easy. We say we just have one set, different objects in this set. And this set we call M. So that's our original set. Then we can consider, well, we have some points, some elements which are part of M, and we have some which are not part of M. That's those ones, for example. And well, if we consider all possible objects, so those which are inside of M and those which aren't, we get this whole space. This is called the sample space. We write this with a large omega symbol. So the sample space contains all the elements which are in any way possible. So for example, if you think about the typical six-sided dice, we have actually 6 elements in the sample space, which is 1, 2, 3, 4, and 5, and 6. So this is, in this case, the sample space. And well, if I know the sample space and I know a specific set which is part of the sample space, well, any set is part of the sample space. But if we consider this here as M, and the set M does not represent the whole sample space, then whatever is in the sample space, but not in M, so here, this area, this is what we call the complement of M. And well, if we have M, we have the complement of M, we can directly define the sample space as M and the complement of M. So both of them taken together make up the sample space. We also know that the complement and M do not intersect. Here it looks like M is situated inside of the complement, but no, this is not the case. So they do not intersect, they do not share any objects. So the complement and the set itself, they are so-called disjunct sets. Disjunct means they do not share any objects. Okay, so we defined the sample space, we defined the complement of a set. We can take a look at a small exercise on this, small example. For this we have here a set of the numbers 1, 3, and 5, and the whole sample space of 1, 2, 3, 4, 5. Then, well, you might imagine what happens next. We want to have the complement of A with regards to the sample space omega. So that's all the numbers which are in omega, but not in A. And well, here that's the 2 and the 4. So the complement of A, that's 2 and 4. Well, this already is the small example on this topic. So we can switch to the next idea. And for this next idea, we first consider two different sets, the set M and the set N. Each of them have different objects. And we see in the middle, there are two objects which are part of M and of N. And if we consider this area here, those two objects, that's basically where the sets N and M intersect. And that's why we call this part the intersection of M and N. And when we talk about intersections, we mark this with, well, this looks like a flipped U. This means intersection, so is in M and is in N. Okay, so we know the intersection. And well, we can also get back to what I mentioned 2 slides earlier, where I said, well, the intersection of a set and its complement is always the empty set, because they do not intersect. So if you have two disjunct sets, the intersection is always empty, is always the empty set. Okay, so with this in mind, let's go on to the next part. Next part is an example on this, on how to calculate the intersection. So for this, we have two sets, set A with the objects 1 and 2, and set B with the objects 1, 3, and 4. And our task, well, find the intersection of A and B. So find those objects which are in A and in B. And well, we start with the smallest set, so here with the A. We check the 1 is in A, the 1 is in B. So the 1 will be in the intersection. Then we only have 2. 2 is in A but not in B, meaning 2 will not be in the intersection. And well, we checked all the values of A, so we can already conclude that the intersection only contains the element, the object 1. That's all there is to this example with the intersection. Okay, so this was the intersection. Now we're doing the exact opposite. Again, we consider our two sets, M and N. And what we do here is we consider all the objects which are either in M or in N. So basically before we said they need to be in M or N. Now we go with they need to be in M or in N. Meaning we consider this whole area here. And well, if we consider this area here, we call this the union of M and N. And this is marked with an, well, a bit stranger U. In some cases it's just replaced with a large U, but this is the sign for the union. If we consider the union, we have to take care about one aspect. That's the two elements in the middle. I go back one part. We have two elements in the middle, that's the two in the intersection. If we were to count all the elements, we would count those elements twice. This is actually a problem. So every set can contain only one copy of each object. So a set could not be like 1, 1, 1, 1, 1, 1, 1. We would only record the 1 once. If we go here and calculate the union, we would count these two elements in the intersection twice. So we have to actually omit one version of each of those objects when we calculate the union. So we take all the stuff which is only in M, we take all the stuff which is only in N, and we take once the things which are in M and in N. Well, this problem only arises if the intersection is not empty. And well, we keep this in mind because we're going to get back to this aspect when we talk about the probability theory. Because there we have the so-called addition theorem, and this uses exactly what I said here. If we calculate the union, we have to take care that we do not calculate or consider those 2 points in the intersection twice. Okay, let's have a short example for this. Here we have again two sets, the two sets we had before. A with the elements 1 and 3, B with the elements 1, 2, and 4. And if we consider the union, we first start, we have the 1. Here we have 2 1s, so we count this only once. So 1 is part of the union. Then in B we have the 2. In A we have the 3, and in B we have the 4. So we have the elements 1, 2, 3, and 4. But, as I said, only 1, 1. And this looks as here. 1, 1, then the 2, 3, and 4. So this was already the first 3 parts. So there's only one aspect left, which we haven't yet talked about. And for this one, you see, again, the same 2 sets. And what we're doing now is basically we're cutting out the set N out of M. So we consider only the stuff which is purely in M. And that's this part here. So we only want to have the stuff which is inside of M. So we exclude the two elements which are in M and in N. And we're calling this, what remains, the so-called difference or difference set, or M without N. That can be seen like subtraction, what we're going to do here. We subtract basically all the elements which are part of the other set as well. Let's illustrate this with a short example. Here we have the two sets 1, 3, 4, 5 and 1, 2, 3. So if we want to calculate the difference, or A without B, this is just, we take a look if any of the elements of B is in A, and those which are, we just omit from A. So we see we have the 1 in both of them, the 2 is only in B, so the 2 doesn't matter, and the 3 is in both of them. So we erase 1 and 2 from set A and are left only with 4 and 5. And that's then our difference set, or our difference. And well, that's with the basic operations all there is to go. So we have the complement, sample space, we have the intersection, the union, and the difference. However, there are two a bit more sophisticated rules to go with, and that's the so-called DeMorgan Rules. The DeMorgan Rules look as follows. So what happens if we take the complement of the intersection or the complement of the union? And well, the interesting insights from DeMorgan were that we basically switch the set operator. So an intersection becomes a union becomes an intersection. For those of you who think, well, this looks a little bit like the distributive rule for negative numbers. So I multiply A plus B in parentheses with a negative number. And then, well, each number becomes negative. In particular, the A inside changes sign. Or maybe people thinking about, if I have an inequality and I multiply this inequality with a negative number and it changes the sign. Well, that's similar to what we are doing here. It's a different field, but the operations by itself, they look similar, they work similar. And well, just to be sure that this also works out fine, we're going to do this with an example step after step. So we start with the first DeMorgan rule. We consider the two sets here, M and N, which are 1, 2, 3 and 2, 3, 4. And we start, as I said, with the first DeMorgan rule, which here requires us to also have a sample space, which is, well, obviously 1, 2, 3, 4. And then we first start with the intersection of M and N. And we see this is the numbers 2 and 3. They are in both of them. Then we take the complement of 2 and 3. This leaves us with 1 and 4. So those are the numbers which are in the sample space, but not in the intersection. So we covered the left side of the rule. So now start with the right side. For this we need the complement of M and the complement of N. Well, the complement of M, what is in the sample space, but not in M, that's only 4. And the complement of N, that's only 1. And then, well, that was the first part. We need to have the union of the complement of M and the complement of N. The union here is 1 and 4. And then we see the left side, 1 and 4, the right side, 1 and 4. So they are the same. So at least with this example, the DeMorgan rule works. And well, you can believe me, this works for other examples as well. Okay, so much so good for the first example. Let's now consider the second DeMorgan rule. So for this one, again, we start with the same two sets. We have the same sample space. Now we start again with the left side. So we're going considering here the union of both of them. Union of both of them with all the numbers 1, 2, 3, 4. Then we consider the complement of the union, which leaves us with the empty set. Okay, we have the empty set, and in this context, empty set does not mean we, for some miraculous reason, we get an element of 0, just means the set is empty. There is nothing inside. So 0 is essentially an object. An empty set does not contain any objects. So the same thing here. All the elements are already in the union, so there's nothing in the sample space which is not in the union. So the complement here is the empty set. Okay, then start again with the right side. Again, we need the complement of m and the complement of n. Well, we had those from the slide before as 4 and 1. And then we need the intersection of those two sets. So the elements which are part of the complement of m and part of the complement of n. And well, 1 and 4, they do not share any elements. So here the intersection is the empty set as well. Now we see the left side results in the empty set, the right side results in the empty set. So it seems to make sense in this case as well. Again, as I said, you can trust me on this works, or you might look up the mathematical proof, but all of the rules here, they actually work in a fashion I've shown them here. And the examples are just to illustrate them, to illustrate how they might be used in a practical context. Well, this already was everything I wanted to talk about in this unit. So I hope you enjoyed it. And other units you can find via the course on Statistics 2 or via the corresponding playlist. I say goodbye and see you next time.